So hello and welcome to the lecture number 6 of the year cycles, and today we shall discuss some numerical problems regarding dual cycles. In the previous lecture session we had discussed the concepts of dual cycles, and now let us see what are the problems uh, we can understand. So let us start with the first problem. An year standard dual cycle has a compression ratio of 60. So you can simply write RV is equal to 60. And compression begins at 1 bar 50 degree Celsius. Compression begins at 1 bar 50 degree Celsius. The maximum, I will rewrite these terms later on because I need to draw the diagram. The maximum pressure is 70 bar. The heat transferred to air at constant volume is equal to the heat transferred at constant pressure. Estimate the pressures and temperatures at the cardinal points of the cycle. That means you need to find out the pressure and temperatures of all the specific states. And secondly, you need to find out the cycle efficiency. So how you are going to do this? Okay, so just let me give me some time and I will draw the diagram so that it will be easier to explain things. Okay, so I have drawn the dual cycle over here, and you can see these are the following processes. So this is your reversible adiabatic compression, then the heat addition in constant volume, heat addition in constant pressure, then the reversible adiabatic expansion, and thereafter the heat rejection. So you can write Q1 and you can write Q1 over here. So now the question is, you need to find out the pressures and the temperatures at the cardinal points of the cycle. The cycle efficiency needs to be calculated also. So here you can see that the maximum pressure is given as 70 bar. Now if you just go through this diagram, you can see that this is your maximum pressure, which is also equal to this pressure and the pressure at this state. So P3 is equal to P4. P1 is already given in this problem. So you can easily find out that P3 is equal to P4 is equal to 70 bar and P1 is equal to 1 bar. Then what are the questions you need to find out? So you need to find out what is P2. First of all, you need to find out P4. Okay. Then you need to find out T2 because T1 is only given here. You need to find out T3. You need to find out T4. And you need to find out T4 and you need to find out T5. So these are the questions, and ultimately you need to find out the efficiency of this dual cycle. So this is our question. Okay, we need to find out two specific pressures, these four specific temperatures, and ultimately we need to find out the efficiency. So to start with, if we follow this process 1 to 2, then it is simply a reversible adiabatic expansion process. That means PV to the power gamma is equal to constant. So PV to the power gamma is constant for this process, right? So P1 to the power gamma would be equal to P2 to the power gamma. Very easy to understand. That means if you write P2 by P1, then it would be simply written as V1 by V2 to the power gamma. Right. Now the question is, what is V1 by V2? V1 by V2 is nothing but this compression ratio. This is what compression ratio is. So it will be simply replaced by 16. I would just simply write 16 over here because V1 by V2 is nothing but the compression ratio. And what is the value of gamma for year? For year, it is taken as 1.4. So we have discussed these things a lot of times, and I believe you have no problem in understanding this. So this P1 is nothing but 1 bar. So therefore, we can easily calculate this pressure P2, and if you just simply calculate this, you will find that P2 becomes 48.5 bar. Okay, so now you can see that we have already solved a question here. So we have found out this P2 as 48.5 bar. Okay, so the first part has been calculated for the pressure. Now coming to the temperature at state point 2. So how we can find it? So if we just modify this relation, you know this relation can be expressed as T into V to the power gamma minus 1 equal to C. That means you can write simply T2 by T1 as V1 by V2 to the power gamma minus 1. That is as easy as it seems. So now again doing the same thing, V1 by V2 is nothing but the compression ratio. So what we can do here, we can simply write 16 over here, because V1 by V2 is nothing but the compression ratio. And you know T1 is what? T1 is already given as 323 Kelvin. So T2 would be 323 into 16 to the power 0.4, because gamma is 1.4. Subtracting 1 from it, it gives 0.4. So if you do the calculations, you will find that T2 would become, so you will see that T2 would become 979 Kelvin. Okay, so you see that it would become 979 Kelvin. So 979 Kelvin. Okay, so now after finding T2, what will be our objective? So we have found out two specific things. One is the pressure and another one is the temperature at state point 2. Then what is our next objective? What should be our next objective? So let us try to analyze the process 2 to 3. What is this process? It is heat addition but at constant volume. So you know that in this process, what would be the prevalent relationship? It would be P3 by P2. You can write P3 by P2 equal to T3 by T2, right? Because the volume is constant in this case, so pressure would become proportional to temperature. That is as simple as it is. Now you know P3, right? P3 is the maximum pressure and it is given by 70 bar. So if P3 is 70 bar, then you can replace it 70. We have already calculated P2 and it was found to be 48.5 bar here. So 48.5, right? And we have already calculated T2 also. So T2 is 979. Now then it becomes easy to find out T3. So therefore you can find out the value of T3 and ultimately you will get the value of T3 as 1413 Kelvin. Okay, so T3 would be simply 1413 Kelvin. Okay, so it would become 1413 Kelvin. Now come into the next part. So we have achieved this, and this. We are left with T4, T5, T4 and this efficiency. Now if you see this statement over here, the heat transferred to air at constant volume is equal to the heat transferred at constant pressure. So what does it mean? That means the heat transferred in both the cases are in constant volume as well as constant pressure. That means the heat added here for this process is equal to heat added here for this process. So you can write simply as Q 2 to 3 is equal to Q Okay, so Q2 to 3 can be written as Q3 to 4. Now the question is, how do we calculate this Q2 to 3? Is it possible to calculate for us? Yes, it is, because Q2 to 3 would be simply calculated as Cv into T3 minus T2. Since this is a constant volume heat addition, if you go through the previous lectures, you will find that the internal energy change is equal to the heat transfer here. Okay, so what is the value of Cv? Cv for air is always 0.718. Please remember this value. Okay, so 0.718. Now you know T3 is 1413. So we have calculated it, and we have also calculated the T2. It is found to be 979 Kelvin. So ultimately you will find that it becomes 312 kilojoule per kg. Since the mass is not given, we are calculating the heat transfers per unit mass. Okay, so Q2 to 3 can be calculated as 312 kilojoule per kg. So the total heat addition, if we take total heat addition as Q1, so it would be Q2 to 3 plus Q3 to 4, right? You know this thing, for dual cycle heat is added in this process as well as this process. So the total heat added would be sum of these two, and it will become 624 kilojoule per kg. Okay, so I will leave this data here because it will be required when we move on for the calculation of efficiency. So Q1 is equal to 6. Okay, just let me rewrite this thing so that we can use it when it will be required. 624 kilojoule per kg. I think you have found out the way how I have calculated the heat addition. Okay, now coming to the Q3 to 4. That means we are bothered about the heat addition for the process 3 to 4. And if you concentrate on the process 3 to 4, you will understand that it is nothing but a constant pressure heat addition. So what would be the formula? The formula would be simply like this: T4 minus T3, right? It would be simply like this for the heat addition here. It is a constant pressure constant pressure heat addition. So the formula would remain as it is. So Q3 to 4 was found to be 312. Okay, so Q3 to 4 was found to be 312. So 312 divided by Cp. What is the value of Cp for here? It is 1.005. I believe you remember this value as we have encountered the value so many times for this module. Now, so it would be equal to T4 minus T3. And what is this T3 here? This T3 is nothing but the 1413, right? So 1413. Then how we will be calculating this? So if you just do this rearrangement, that means you can understand that, you can easily understand that plus 1413 would be equal to T4. Okay, so now I believe you have your calculator on your hands, and you will find this T4 would simply become and it can be calculated as 1723 Kelvin, right? It is very easy to calculate then. So T4 can be found out in this way. Okay, so since we have found out T4, we can leave it here. Okay, so T4 is found to be 1723. So you can see that this is the maximum temperature of the cycle. That means when the combustion is completed, when the heat addition is completed, we find that this is the maximum temperature. Okay, now So T4 is also completed. So what we have left to do? We need to find T4, we need to find T5, and we need to find this eta dual. That means the efficiency of the dual cycle. So what I'll do, I'll just clear this off, and now let us focus on finding the value of uh, T5. So how we can calculate the value of T5, right? So T5, if you concentrate on this process, then it is a reversible adiabatic expansion, right? So the equation is T into v to the power gamma minus 1, right? That is equal to constant. So for this process, what will happen? You can write T4 by T5 is equal to V5 by V4. Okay, so this can be represented as V5 by V4 to the power gamma minus 1. Now the question is, do we know the value of V5 or V4? No, we don't know. We know the value of T5. We know the value of T4, right? It has found as 1723 Kelvin. So we need to first find out the value of V5 by V4. So how it can be done? So if you look for this process, you will see that this is a constant volume process, right? So V5 is equal to V1. So V5 by V4. Our objective is to find out the value of V5 by V4. How we can do this? So we can write it as V1 by V4. We can simply write it as V1 by V4. And if we just do this thing, V1 by V2, if we write this thing in this way, V2 by V4, then there is no problem. I am simply multiplying and dividing this equation by V2. Okay, so V1 by V2 into V2 by V4. Now if you just concentrate on this process, you will see that V2 and V3, they are synonymous, they are the same thing, right? So I can simply write V3 over here. The question is, what is this V2? This V2 is nothing but the compression ratio, so it would be simply 16. Now the question is, what is this V3 and V4? What is this? This is the cutoff ratio. How we can calculate this cutoff ratio? So here, what we need to do, we need to study this process. This is a constant pressure heat addition, right? So that means for this process, volume would be proportional to the temperature. So for this process, volume would be proportional to the temperature. So V3 by V4 would be equal to T3 by T4, nothing else. Since it is equal to this, and we know what is the value of T3. T3 has the value of so there is no need to worry because we can easily find it out. Okay, just simple use of calculator here. Okay, so after finding out V3 by V4 as 0.82 and putting the value of this 0.82 here, we can get the value of V5 by V4 as 13.12. Okay, so after finding out the value of V3 by V4, and V3 by V4 is nothing but the cutoff ratio. Okay, the reciprocal of cutoff ratio, because cutoff ratio would be V4 by V3. So this cutoff ratio, the reciprocal of cutoff ratio becomes 0.82, and we put this value 0.82 here, and ultimately we get the ratio V5 by V4 as 13.12. Okay, so I will just clear these things here. So this V5 by V4 becomes 13.12, and what do we do here? We put the value of T4 as 1723 Kelvin divided by T5 is equal to 13.12 to the power 0.4, and thereafter we can find T5 as 1723 by 13.12 to the power 0.4, which ultimately gives T5 as 615 Kelvin. Okay, so thereafter we can find out the value of T5. Okay, still we don't have the value of So now we can find out that we have calculated these four temperatures. We are only left with this pressure P4. I'm sorry, this P4 is already known to us. We are left with P5 actually. We don't know the value of P5. So concentrating on this process, okay, this is a constant volume process, right? So what happens? The pressure would only depend on the temperatures. So we can simply write P5 by P1. This P1 is equal to 1 bar, mind it. So there is no such importance here. So it would be T5 by T1, right? So T5 is equal to 615 Kelvin. T1 is equal to 323 Kelvin. So you will find that this P5 or the pressure at state point 5 would become nothing but 1.9 bar. Okay. So P5 would become 1.9 bar. So therefore we can easily calculate the requisite pressure and temperatures at the cardinal points of this cycle. Now we are only left with the calculation of the cycle efficiency. Okay, so that is the thing which we are still left with. So how do we calculate? So you know, efficiency of a dual cycle, it is nothing but the heat addition and the heat rejection, right? So it is 1 minus Q2 by Q1. So we have already found out the value of Q1, that was found to be 624 kilojoule per kg, if you remember. Now the question is, how do we find out Q2? Again, very simple. Since this is a constant volume heat addition, I'm sorry, this is a rejection over here. Constant volume heat rejection. You can simply go through this formula. Cv T5 minus T1. Right, it would be Cv T5 minus T1. So what is T5? 615. What is T1? It is 323. What is Cv? It is 0.718. So ultimately you will find that this Q2 will be calculated as, okay, so this Q2 can be found as 209.6 kilojoule per kg. And now we'll be able, it is easy to calculate the efficiency, right? So the efficiency can be found out putting these values here. 209.6 divided by the 624, which we found as the heat addition, and ultimately you will see that the efficiency of this dual cycle would become 66.5%, or you can also write it as in terms of this decimal fraction, which can be written as 0.665. Okay, so thereafter you have completed this problem, and we would complete this problem here, and we will go on to a different topic, a different analysis here. We would like to compare auto, diesel and dual cycle from the point of view of efficiency from two aspects. The first aspect being when we have considered that both these all these three cycles have the same compression ratio. When these cycles have the same compression ratio, then which cycle will provide you the maximum efficiency? So this is the first aspect from where we would like to compare these three cycles. And the second aspect is that we would like to compare the efficiency of this cycle from the point of view where we would like to see if the cycles have the same maximum temperature and pressure. If the three cycles have the same maximum temperature and pressure, then what will be the efficiency? Which cycle will give you the maximum efficiency and which one will give you the minimum? Okay, so let us check that how it can be done. Okay, so here you can see this diagram over here. So here this is this Here you can see there are three specific cycles, so I need to write it down here. So if you consider 1 2 6 5, so if you consider this cycle 1 2 6 5, which cycle is this? From the common sense you must be able to answer this. So it is nothing but the auto cycle. Okay, so this is nothing but the auto cycle. Now coming to the cycle 1 2 7 5, 1 2 7 5, which cycle is this? Can you think of it? Which cycle will be this? This is nothing but the diesel cycle, right? Very easy to understand. And the last one I believe you have already identified which cycle I am talking about. So it would be 1 2 3 4 5. 1 2 3 4 5. So 1 2 3 4 5. That is the dual cycle. Okay, so we have compared these three cycles from the same compression ratio. Okay, the compression ratio is same for all these cycles, and now we have compared them. Okay, so this is the representation in PV diagram, and this is the representation in the TS diagram. Right, now if you remember the concept of efficiency, then you must remember efficiency is nothing but the W net by heat input, right? It is W net by Q1, that is equal to the efficiency. So what is this W net? W net represents the area over it. Okay, like if you consider this area, this area if you consider, then this is the area for the diesel cycle. Okay, so this is the area for the diesel cycle, and with this area if you add it at this area over here, then this total area would give you the area for the dual cycle. And again if you go on adding this portion, this triangular portion, then you will get the area for the auto cycle. So obviously you can understand auto cycle has the maximum area, then the dual cycle, then the diesel cycle. So from this aspect you can say that the auto cycle will have the maximum efficiency here. So eta auto will be greater than eta dual. So just from the perspective of area, it gives you the maximum work output. Under PV diagram, the area represents the net work done. More the area, more the work done. Okay, so obviously auto cycle have the maximum work done. So therefore, you can find this relationship. Okay, so what is the relationship here? Auto cycle will give you the maximum efficiency when we are comparing these three cycles for the same compression ratio. Okay, auto cycle will give you the maximum efficiency. Now, okay, and diesel will give you the minimum. Now, how does it change when we apply the same thing? Apply the same thing for the maximum temperature and pressure. Okay, so here you can see again a pictorial representation over here, and you will be understanding that this cycle. Okay, so I need to write it down again here. I'm sorry. So 1 2 7 4. 1 2 7 4. Which cycle is this here? Can you answer it? Yes, it is diesel cycle. Right, you are. So it would be diesel cycle. So it will be diesel cycle. Now coming to this point, 1 2 3 4 5. This is easy to understand. You know that the heat addition is taking place in two separate processes, so it would be nothing but the dual cycle. So it will be the dual cycle. Okay. And coming to the next one, 1 6 4 5. Which cycle is this? This is nothing but the auto cycle. Right, you are. So it is nothing but the auto cycle. Now the same philosophy will be used here as it was used earlier. You can see that this auto cycle have the minimum area here. So when we are comparing these three cycles, you can understand that this is the maximum pressure. Okay, this auto cycle has this maximum pressure over here. So for auto cycle it would be P4, for diesel cycle it would be P7. But both of them has the maximum pressure, and it is same, it is exactly equal. And comparing from the point of view of temperature, if you see this compression ratio, if you see this TS diagram over here, then you can find that this is your auto cycle. Okay, so what is the maximum temperature? It is T4. It is T4 here, and here for all these three cycles the maximum temperature is fixed, and all these cycles have the same maximum temperature. Still, you will understand, I think you have already understood it, that auto cycle has the minimum area, whereas dual has the next minimum here. Okay, so dual always lies in between. And when we compare the cycles from the point of view of uh, maximum pressure and temperature, you can understand that diesel cycle, right? So this diesel cycle has the maximum area, whereas auto has the minimum. So for same maximum pressure and maximum temperature, what happens? Eta diesel gets the first place. Okay, so diesel is the champion over here. So eta diesel is greater than eta dual. Okay, eta diesel is greater than eta dual, and ultimately the loser is auto here. Okay, so eta diesel is greater than eta dual, greater than eta auto. So when we compare these cycles from the point of view of same maximum pressure and maximum temperature, we get to know that auto cycle will give you the minimum efficiency, whereas diesel will give you the maximum efficiency. Okay, so I think I have cleared this thing. For the same compression ratio, auto gives you the maximum efficiency, diesel gives you the minimum efficiency. But for the same maximum pressure and maximum temperature, it is exactly reversed. It is exactly opposite. That means auto becomes the minimum efficient cycle, whereas diesel is a maximum efficient cycle. Okay, so with this, we'd like to end our session here. Thank you, and see you all in the next session, where we will start discussing about the Brayton cycle. Okay, till then, goodbye and thank you.